NASA currently develops an engine system which may violate physical laws to achieve close to light speed velocities. Traveling to Mars in only 13 minutes and Alpha Centauri in human life duration is possible without taking the centuries-long journey. This isn't science fiction. The helical engine stands as an experimental device which fights against all existing space travel knowledge. The helical engine appears to disregard one of the basic laws of physics by breaking the conservation of momentum rule. Does this revolutionary technology actually work, or does it belong in the category of failed M-Drive projects? We explore the scientific findings combined with doubts and remarkable features about NASA's upcoming near-light speed propulsion system. This article will send star systems ablaze with information about breakthroughs to reach near light speed. The M-Drive represents the technological source which initiated this controversy. 2 decades ago, British engineer Roger Scheuer suggested his microwave thruster produced thrust while using no propellant. According to Scheuer, microwaves reflected inside an enclosed space could power spacecraft propulsion while emitting any exhaust products. Dr. Stanis Lebowski of NASA's Glenn Research Center dismissed the M-Drive as impractical. Harold White at NASA Eagle Works Lab conducted a test of the prototype space drive system in 2013 and documented its production of 0.1 newtons of thrust, which could propel a satellite. Scientists cautioned the public against premature celebration, even though people were going wild about what they had heard. The M-Drive achieved a minimal success by producing thrust equivalent to an eyelash weight while directly contradicting scientific laws. Scientists expressed doubts that heat and vibration signals produced false results in the M-Drive experiments. The later Chinese announcement about testing similar technology generated inconsistent results that caused observers to laugh at the attempts. Yet the hype didn't die. Why? The reason people remained interested in the technology is because if it proved functional, it could create time and cost advantages for space exploration. We will determine why the helical engine is important by looking at functioning ion engines as the foundation. Remember Star Wars' sleek starships? Real ion technology that NASA created started from the concept illustrated in their fictional spacecraft designs. An ion engine produces thrust by releasing ions from its rear output instead of using detonable fuel. The engine system provides astounding efficiency by reaching ion acceleration rates of 25 kilometers per second. The thrust generated by this engine proves insufficient because it provides only as much force as a person would experience while using a solitary sheet of paper. Science missions have used their thrust capability to achieve historic breakthroughs. The ion-powered Dawn spacecraft from NASA traversed to orbit all the way to both Vesta and Ceres asteroid planets during its 2007 launch mission. During its 2003 launch, the Japanese Hayabusa mission returned asteroid samples to Earth powered by ion thrust. Even SpaceX employs ion thrusters in its Starlink satellites for precise orbital adjustments. But ion engines are slow. The transmission to Mars would extend into months instead of days using these methods. Now, NASA engineer David Burns' wild idea, the helical engine. A circular loop containing swift ions would achieve exceptional velocity speeds close to the speed of light. The theory of relativity by Einstein specifies that the mass of the ions would rise, which produces thrust, while generating zero exhaust. Despite the claims of Burns about reaching 99% speed of light, some experts dismiss this technology because they believe it breaches momentum fundamentals. Burns presents an unconventional perspective about the engine design, which he states circumvents physical laws. The helical system moves ions in rotary motion, which makes their mass propel the engine forward. The critics challenge this theory when they ask for visible exhaust to justify the mechanism's operation. Where's the momentum going? The spaceship uses such tremendous speeds that it creates motion by interacting with the fabric of space-time, according to Burns, even Einstein would have doubts about. Let's break it down. According to conservation of momentum, there exists an unbreakable law which states no one receives something for nothing. Becoming mobile requires a backward motion of some kind. The engine system claims an ability to dodge this requirement. According to Burns, his model can operate due to the principles of relativity, yet the scientific community does not adopt this interpretation. For minimal thrust, the engine would require both 200 meters of length and 165 megawatts of power. The process of reaching Mars in 13 minutes requires years of acceleration time for the voyage. At near light speed levels, time decelerates, so astronauts become older than Earth residents while protective radiation shielding remains unmanaged. Unresolved, Burns expresses his conviction that this design serves as a proof of concept. We're pushing boundaries. Scientists have yet to prove the theoretical nature of the helical engine despite other advances that have become reality. The use of nuclear thermal propulsion, NTP technology, allows spacecraft to reach Mars in 3 months by utilizing reactor-generated heat to vaporize hydrogen. Draco under NASA plans to conduct tests of NTP engine technologies before 2025. The ion engine technology continues to advance, while ESA's Bepicolombo spacecraft relies on these engines during its challenging exploration of Mercury's hot environment. The space technology company Starlink implements ion technology under the direction of Elon Musk. We're in a space race 2.0. Governments, together with private firms, continue to allocate billions of dollars. Has the possibility of achieving light-speed travel ever become achievable? The story of the M Drive reveals human exploration of uncharted territory. Though it faced strong resistance, Scheuer's theory pushed scientists to question how propulsion could be achieved. None of the 0.1 Newton thrust values measured by Eagle Works proved the M Drive's existence according to NASA standards. Media outlets hyped up the findings while disregarding the actual complexity of the results. China made multiple claims of producing 2.4 newtons of thrust, but scientists dismissed them because of their conflicting data measurements. The Earth-based tests eliminated any possibility to identify the engine's real performance because they took place under terrestrial gravitational conditions. The M-Drive legacy represents how complete doubts prove valuable in inspiring development from seemingly unrealistic concepts. Through his theory, quantum inertia, physicist Mike McCulloch determined that the thrust results from quantum vacuum fluctuations. The unverified theory demonstrates that unconventional concepts occasionally stimulate scientific progress. The M-Drive failure generated better vacuum chamber designs along with improved measurement accuracy, which supported other scientific tests. The transformation of ion engines from science fiction to real-life application required significant determination. Philip Nolan introduced the idea in his novel Armageddon 2419 AD, published in 1942, through his description of ionic rockets powering spaceships. The first manifestations of real-life ion engines emerged during the 1950s, even though Star Trek and Star Wars brought them to popular attention. NASA executed the first ion engine experiment from Space Electric Rocket Test 1, SERT-1, between 1964, when it operated for 31 minutes. The launch tests demonstrated that ions could effectively power spacecraft, so the United States stopped developing ion technology because of funding reductions. After the Soviet Union abandoned its exploration programs, they continued working on innovative space engine technology by creating the SPT-100 to maintain satellites in position. Deep Space One from NASA became the first space mission that depended completely on ion propulsion when it launched in 1998. The spacecraft utilized its engine for a total of 16,250 hours, during which it explored both the asteroid Braille and the comet Borrelly. The European Space Agency proved the versatility of ion thrusters by achieving lunar orbit using their Smart 1 spacecraft. Thank you for joining us. If you enjoyed this exploration, don't forget to hit the like button and share your thoughts in the comments below. Stay curious and keep exploring.